Welcome back to our discussions of thermodynamics and chemical energy. I noticed that nobody's been watching our videos, so I'm wondering about the utility of this. It could be simply that you were distracted getting the exam ready, getting ready for the exam. Now that that is over, I encourage you all to go back and watch the videos that I've posted so far. They are linked on the Blackboard page. For the most part, where I've sent these out via email, I'll send this out again and make sure that they're posted. Do hit subscribe if possible, so that you get automatic updates to these. And also it lets me know that you are actually keeping up with this course. I understand there were some technical issues with the exam. Hopefully you got through that okay. Please communicate those with Professor Larson, who has been in charge of setting all of that up. He's done a great effort, and of course with everything else there's always a chance that there's something happens, and probably something did happen. Hopefully it was a minor thing instead of a major thing. If it was a major thing, please communicate that to Professor Larson, and we'll figure out what we can do. Okay, so we're going to finish up today looking over at the schedule here. We are on roughly right into here in the discussion of chemical energy. We finished up our discussion of chapter 7, and we're going to move on to chapter 8. Before we do that, we're going to talk about what's called lattice energy, going back to chapter 4, and then move on and talk about gases. So I will do this in 2 separate video postings. Today we'll only discuss lattice energy, and then in my next posting I will discuss gases, so that we can have a separation between the two. They're basically related concepts, but different enough that it's worthwhile putting things in separate videos. So today we're going to recap what we talked about with Hess's law. Hess's law is the statement that I can calculate, or I can understand, the heat of formation, the heat of a reaction, by looking at the change in the enthalpy between reactants and products. And again, enthalpy is this thermodynamic potential. It's a state function. It only depends upon the thermodynamic state, temperature, pressure, volume of a given system. I should say temperature, pressure, volume, and composition of a given system. And by looking at the changes in enthalpy, I can understand the heat and energy associated in going from one thermodynamic state to another thermodynamic state. Now I emphasize this issue of independent of pathway. It's a state function. It only depends upon the temperature, pressure, volume, and composition of the system. So if I change composition, there's an enthalpy change. If I change the temperature, there's an enthalpy change, and so on. Typically, in chemical systems, we do things under the condition of constant pressure. So under that condition, the enthalpy is really a measure of the heat that has been given off or liberated or taken in or absorbed by a chemical reaction. So it's an important indicator of the energetics of that chemical reaction. I'm not going to talk about other thermodynamic potentials. I was just sketching out from my own thoughts a little bit below whether or not I would talk about entropy and other thermodynamic potentials, but I think I'll defer that for the second course in Foundations of Chemistry, and as not to confuse things today. I can, if you wish, post a separate video on thermodynamics, a much more detailed discussion of thermodynamics and the different kinds of thermodynamic potentials, Helmholtz potential, Gibbs energy, and so on, but we'll not do that today. So let me pull up our slides. So what we want to talk about today is go back and look at the concept of lattice energy. Now I sketched out beforehand some things to think about with lattice energy. So again, looking at this from a chemical reaction from a thermodynamic viewpoint, the only thing that matters is the initial state and the final state and their composition. So if I want to understand the stability, or more or less really the stability of something simple like an ionic system, like salt, I can understand the stability of that by looking at the energy that's given off when I go from its most associated form, gaseous sodium chloride, for example, fully ionized sodium ions plus chlorine ions to form solid sodium chloride. That is the enthalpy of formation. It's always a negative because typically things, if something forms, if you've lowered the energy of that system, in a sketch here, you can imagine I have a bunch of positives and negative ions floating around in a gas, and then you lower the energy. The system lowers its energy by going to this much highly ordered state. Now you might think, well, doesn't the second law of thermodynamics say that entropy increases? How is this possible? That the system would spontaneously go from its maximum entropy state, which is everybody's ionized and moving around freely, to its lowest entropy state of a nice packed, closest packed solid. Well, the entropy of the universe is increasing because I liberate a lot of heat when I do this. I've gone from something that has heat here and to something that has very low heat, and in doing so I liberate a lot of heat. And that heat that's liberated and going from here to here is the enthalpy of formation. Okay, so in a sense of a picture, I go from a high energy state, a high enthalpy state, to a very low enthalpy state. This being the standard state of sodium chloride, for example. This is not the standard state of sodium chloride at 300 degrees Kelvin, or 298.15 degrees Kelvin, the standard state, standard temperature or pressure, and pressure. This solid sodium chloride is the standard state of sodium chloride. There's an energy difference between this. So if you could look at it the other way around, I could say, well, how much energy would be required to take sodium chloride, table salt, and fully ionize it in the gas phase? And it would require this much energy, the opposite of this. So a very large positive amount of energy would be required to go from here. So this delta H is going downhill. Going from here to here is uphill in terms of the delta H. Okay, so the example we're going to look at is, let me skip this, is that of lithium fluoride. So the reaction of lithium fluoride is basically, we look at the reaction of lithium plus fluoride. It's a fairly violent reaction. Lithium is very reactive. Fluorine is very reactive. The lithium fluoride is very stable salt, and it follows a particular sequence. And let's sketch out what each one of these steps happens to be. And remember, so here's the reaction. Here's our net reaction. I'm going to look at lithium in the solid phase plus a half a mole of fluorine in the gas phase to form lithium fluoride in the solid phase. Now, again, phase is important, and is it a solid? Is it a liquid? Is it in a gas phase? It's important. So I have to note the thermodynamic state and its physical state all the way through. And again, these are usually done in per molar basis in terms of the product. So we're going to keep everything in terms of per molar. That's why we have a 1/2 stoichiometric coefficient here, because I want to make 1 mole of lithium fluoride solid per molar, delta H per mole. Okay, so how do we do this? So I don't know the actual mechanism for this. It's probably much more complicated, but we can follow a specific route to go from this lithium solid plus fluorine gas phase. Lithium in the solid at room temp at STP is a solid. This is at standard temperature pressure is a gas. Fluorine is a gas at standard temperature pressure. So if I want, this is now lithium solid and a half of a mole of in the gas phase. So that's our starting point. Let's put this over here. For some reason, my camera just went right out of focus. There we go. Okay, that's our starting point. This is our standard state, so that's our starting point. Now let's just sketch out what all is required to do this. So first thing I need to do is to take lithium and sublimate it, make it a lithium lithium in the turn this a little bit so I can turn that this way. There we go. So we're going to vaporize lithium and put it into the gas phase. So this is going to lithium. So we're just going to take the lithium, and that's going to require, this is now lithium in the gas phase. That process is called sublimation, and that requires 161 kilojoules per mole. Okay? And then I'm going to ionize this, and energy is released. We're going to ionize this, and that energy is released, and that's again uphill in energy. It requires energy. This seems rather backwards. Energy is required in order to do that. It's not released. It's a positive quantity. And that requires another 520 kilojoules per mole. Okay, so that is the energy to take that right there. And this is in the gas phase. So the notes are wrong. Energy isn't released. Energy is required to do that. You put energy in. Again, you're going from a bound lithium ion to dissociate it, and that requires 520 kilojoules per mole. It's not a downhill process. That's an uphill process. So there's an error. The notes are in error. Caveat emptor. Okay. Now let's look at the fluorine. The fluorine ions have half of a mole of fluorine, and I need to dissociate it to form 1 mole of fluorine ions, fluorine atoms. So we're going to go uphill in energy from here by 154 kilojoules per mole, and that is going to give me F gas phase fluorine atoms, and then this is a spontaneous process to go downhill in energy to form F minus. This could, it very much would like to have that electron in the gas phase plus, oops, so F plus this electron, that electron, if you want, can appear down here, and this is now spontaneous by minus 328 kilojoules per mole. Okay, so you can see I can start adding together all of these different thermodynamic pathways. So now see I have this guy up here at 520 kilojoules per mole plus all that, and then this thing's down here at, I just went downhill a little bit by, well, to get to here I went uphill by 154 and then down by 328 to get to here, and now I add these guys together, and we can do that here. So the first step, let me write this out as a sequence of steps: lithium solid to lithium gas. This is just accounting. The energy change for this was 161 kilojoules per mole. Okay, these are all in kilojoules per mole. Okay, the next step, step 2, was the dissociation of this guy. Lithium in the gas phase to lithium plus in the gas phase plus an electron. Well, that was 520. 520 kilojoules per mole. Okay, so I can add those together and get me to that point right there. And now the next steps were going again from here and down was that fluorine in the gas phase to dissociate that required energy, 77. So this 154 that was given here is actually the energy that's required to form, to dissociate 1 mole of F2 to 2 moles of fluorine ions. Okay, so if I look at this as an energy V of R, has a radius of separation R, F, F, radius of separation between the two guys. This energy difference between here and here is 154 kilojoules. Okay? So this is the energy required to dissociate 1 mole of that, and so I take half of it. So this is 77 kilojoules per mole. Okay. The next thing, I need to dissociate this guy. I can react that with that electron, F, gas phase, plus an electron. That gives me an F minus 328 kilojoules per mole. Lastly, what I can do is to form the solid. I can take this ion and that ion and combine the two to form lithium fluoride solid, and that is the energy of formation. Lithium plus in the gas phase plus fluorine minus in the gas phase to form lithium fluoride solid. That's the enthalpy of formation of lithium fluoride solid. Minus 1047 kilojoules per mole. So our overall reaction. See, the reason. See, now we can use this. If you think about it, all these pieces of information are things that we can get thermodynamically. See, this is simply the energy that's required to sublime lithium from this to that. Okay, to go from lithium solid to lithium in the gas phase, I have to put in this much energy. If I want to ionize lithium, I have to put in this much energy. If I want to dissociate fluorine, I can put. See, each one of these I can do as a separate experiment. I can do this as an experiment. I can do this as an experiment. This is the ionization potential, or electron affinity, and this is the ionization potential of lithium. Right? This is the ionization potential. How much energy does it take to liberate 1 electron from lithium? Well, it's that much. This is the electron affinity of fluorine. It's liberates 328 kilojoules every time a fluorine gas picks up an electron. It goes down in energy by 328 kilojoules. This is the energy of formation of lithium fluoride solid from the gas phase. And if I add all of these guys together, the overall reaction is lithium in the solid phase plus 1/2 of a mole of F2 in the gas phase. See if you can cancel all these guys out if you wish to give me lithium fluoride solid. And the net is minus 617 kilojoules per mole. Okay, that's of lithium fluoride. So the issue is, you see, all of these guys simply have to add up. I can break this apart into any step that I wish and find the part that I don't know. So this again, this is a separate experiment. This is an experiment. This is an experiment. This is an experiment. That's an experiment, and I can get the energy of that particular reaction if I wish. Okay, so here's the overall picture that I was sketching together. Over here is this whole thermodynamic process going up, 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 and then start going down, 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 down. And again, this is simply, here's my initial, that is my final. The pathway is completely independent. You know, if I react lithium solid plus fluorine, I don't first vaporize lithium and then ionize it, and I certainly don't do this particular reaction pathway. There's probably something far more intermediate. The fluorine gas atoms on the surface of the lithium probably do something and react on the surface, and without ever going to the gas phase. But whatever happens in between here doesn't matter in terms of thermodynamics. Thermodynamics only cares about initial state and the final state. And the overall change, the overall difference between the two is that quantity. Okay, so again, this issue of the lattice energy, which we got out of this last part right here. This particular step was the formation of lithium fluoride solid from lithium positive ion in the gas phase plus fluorine negative ion in the gas phase to give rise to lithium fluoride salt. That is the lattice energy of lithium fluoride. So we can modify the Coulomb law a little bit by saying the lattice energy is some sort of property of the material, and then the R is the bond length of the material. Okay, so the shortest distance between the centers of the anions and cations, and some constant of proportionality. So the more tighter packed the ions are, the greater the lattice energy happens to be. And again, we can look at this in all sorts of different kind of binary systems, you know, and we can understand things from this particular equation quite easily. I mean, we'll sketch out what this equation means again. That might have gone a little bit too fast. So the equation that we're discussing is that the lattice energy, and how I can understand lattice energy of different systems. The lattice energy let's call it ELAT, is equal to some constant of proportionality that depends upon the particular structure of the system. This is, and then Q1, Q2 divided by R. So Q1 is the charge of one ion. So Q1 is the charge of the cation, Q2 is the charge of the anion, and R is the distance of separation. So for example, if I have sodium chloride, remember sodium chloride is a close packed solid of sodium and chloride. There's a bond distance between all of those guys. R, in this case, Q1 is equal to 1, Q2 is equal to minus 1, and the energy of this lattice is going to be minus 1 divided by this distance of separation, whatever that happens to be, multiplied by a constant of proportionality for the fact that, so K depends upon the lattice structure. There are different ways that ions can form a lattice, and usually they form a close packed arrangement. Sodium and chloride form what's called the rock salt arrangement, which is basically, if I were to have a cube, maybe I could draw one out like this. You know, this is a cubic structure. Something like this. All of the chlorines would be here at the vertices, something like this, and then the chlorines are in between. So that I have, if you want to think about this, you know, I would have a 1/4 or 1/8 rather of a little ball here at each corner, right? I have a little 1/8 ball at each corner, right? There's a little 1/8 ball at each corner. So like 1/8 and then a single atom in the middle. So if all of these go through minus, 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 I would have a plus charge here in the middle, surrounded by, it looks like I've got 8 charges, but no, I really have 1/8 of a charge at each corner, and then a little positive here at the middle. So the bond length that we'd be talking about is that bond length between the central sodium and these edged vertices at the chlorine. So it's you know, I suppose you could work this out from geometry. If this is some length of 1, this is square root of 2, and then this is going to be a little bit longer than that. This is you know, whatever this length is. Square root of 2 is what it comes out to be. It's the square root of 2, 1.4 roughly, and so on. Anyway, just you can, this depends upon the geometry, but different ions and different systems will have different lattice structures, and will have different bond lengths between the different ions. Okay, so for example, you know, if I look at MgO, which is +2, and O -2, or 2 minus, 2 plus and 2 minus. Okay, you know, if in this particular case, if they form the same solid, the ELAT is going to be some K times 2 times -2 over whatever bond length that happens to be. Generally, the bond lengths are about the same in each system. If I compare that to sodium chloride, or even lithium fluoride, or any other system, let's say like Na plus F minus, again, you know, I could say that the E lattice is roughly equal to K plus 1 minus 1 over R. Now these bond lengths are about the same. K is the same for each. This is a +1 and a -1, and so you could say that the MgO has roughly 4 times. This is equal to 4 minus 4 K times R, and this is equal to K over R. And so this has 4 times more lattice energy than that. Okay, so you can estimate the stability and how hard something is by simply looking at its lattice energy. Is there a lot of energy that's required to form magnesium oxide versus sodium fluoride, or vice versa? And you can again follow this through thermodynamically, looking at the energy to require to move electrons and so on. And I can write out again a thermodynamic pathway, like we had in Hess's law, like this, and work through all of these. Now, again, oops, where'd it go? Here it is. Oops, I lost it. There we go. And work all of this through again, all of these complicated thermodynamic energies, and I get a lattice energy of this versus the lattice energy of this. And so I can see very clearly from this, you know, tracing out these Hess's law pathways. Um, here I have minus 923 as the enthalpy of formation of sodium fluoride from here. This is the lattice energy compared to the lattice energy of this. And the differences in lattice energy is entirely due to the Coulomb's law. And you notice, yes indeed, this is roughly 1/4 of that. So 4 times 9 is 36 roughly, roughly 10. And this is a little bit less than 4,000 in terms of kilojoules per mole, the lattice energy. So you can understand lattice energy simply by looking at the charges of the constituent cations and anions. So easy way to understand heats of formation or lattice energy is simply to look at the charges themselves. Very strong, large positives and large negatives have much more Coulomb energy, more lattice energy than singly ionized cations and anions, and so on and so forth. So that's a key concept to understanding the binary ionic compounds. Okay, so I want to end this lecture on that note, and I will pick up the next lecture on the gas laws, and we're going to just start discussing gases, the ideal gas law, and so on. And this is a useful concept for understanding not so much chemical changes, but understanding the basics of thermodynamics and the basic atomic principle. So I'm going to end here, and we'll pick up on another slide, another lecture, the remaining topics. So thank you, and let me close out of all of this.